When you are given data as part of a problem, you must assume that the measurement is scientifically honest. That means the measurement is reported with significant digits. And when you calculate, you must state your answer with the correct number of significant digits. This means that you must become skilled in counting the number of significant digits in a given number, and then rounding your answer to the correct number. So, let's review. In a measurement, how many digits are estimated? You're right if you said only one. The last digit is the estimated one. Is it significant? Yes. Significant digits include all measured or certain ones, plus that one estimated or uncertain digit. Well, that seems easy enough, but there is one problem, and that is the zero. A zero can mess up everything if you let it. So, let's learn to deal with the dreaded zero. Check this out.
These students measured the length of the lab table in their classroom with a metric tape and used significant digits to report the measurement as 2.54 meters. How many significant digits does the measurement have? If you said 3, you're right, of course. The 2 and 5 were measured with certainty, and the 4 is the estimated digit. All the digits are significant. Now do this as a class. Convert the 2.54 meters to these units. Divide the effort and write your answers on your board. Your teacher will stop the tape to give you a chance to complete the conversions after you've had time to jot down the units. Here are the answers. Now look at all the measurements. Which digits were measured and which were estimated? If you said the 2 and 5 were measured with certainty and the 4 was estimated, you're right. Stating the same measurement in a different unit doesn't change the number of significant digits. So what is the purpose of all those zeros? They weren't measured and they weren't estimated, so they can't be significant. So what is their purpose? The zeros act as decimal placeholders.
Let me ask you some questions. Can a zero ever be a measured digit? Tell your teacher. Yes, it can. Can a zero ever be an estimated digit? Yes. Sometimes you think that the measurement is right on a line, like 2.5 exactly. So you estimated 0 and get 2.50. So zeros can actually be significant digits sometimes, right? Right. So how do you know when a zero is significant and when it isn't? You could learn some wonderful rules. Here are the rules about significant digits, straight from a physics book. Just listen for now and see if you'd like to memorize them. 1. Non-zero digits are always significant. 2. Zeros between two other significant digits are always significant. 3. Zeros to the right of a non-zero digit but to the left of an understood decimal point are not significant unless specifically indicated to be significant. 4. All zeros to the right of a decimal point but to the left of a non-zero digit are not significant. 5. All zeros to the right of a decimal point and following a non-zero digit are significant. How do you like that? I know. There's got to be an easier way. Well, there is. You just have to look at each measurement with some common sense and one basic question. We'll get to the question in a minute. First, listen to this story.
Picture this situation. Jill is standing in line to get tickets to a movie she really wants to see. She's been standing in line a long time and wants to take a break and run to the ladies' room. But she's afraid that she will lose her place. She spots her younger brother and his friends who are inside playing video games. She gets their attention and asks her brother to help her out. Of course, being a 13-year-old brother, he says, "No way, sis." But his best friend agrees to save her place for a price. Jill agrees to pay him the money and runs to the ladies' room. When she returns, she talks to her brother's friend for a while. A girlfriend sees her and says, "Jill, is he your date, your significant other?" Jill says, "Absolutely not. He's not significant to me. He does not get to sit next to me in the movie or hold my hand or share my popcorn. He is merely holding my place." Placeholders are not significant. Now, what's the moral of the story? When zeros are merely holding the decimal place, they are not significant. Placeholders are not significant. That's the test for determining whether zeros are significant or not. Ask yourself if the zero is merely holding the decimal place. If that is its sole function, is the zero significant?
No.
Right, because placeholders are not significant. When you're trying to decide whether a zero is significant or not, ask the big question. Is the zero merely holding the decimal place? Remember, placeholders are not significant.
Let's look at some measurements and decide whether the zeros are significant or not. Let's start with 83,000 kilometers. Are the zeros merely placeholders? There are two ways to find out. One way is to cover up the zeros and see if the magnitude of the number changes. That means the number gets larger or smaller. If it does, the zeros are placeholders. In this case, when I cover up the zeros, the magnitude of the number changes from 83,000 to 83. The zeros are placeholders, so they are not significant. This number has two significant digits, with the 3 being estimated. Another way to tell if zeros are placeholders is to put the number in scientific notation and see if the zeros disappear. In scientific notation, the power of 10 locates the decimal place. 83,000 equals 8.3 times 10 to the 4th power. The zeros are replaced by the power of 10. When the number is in scientific notation, all you have to do is count the digits, and you have your significant digits. The next number is 0.2341 grams. Remember, we've already talked about zeros before the decimal. No measurement is ever started with a zero. Imagine saying that a green bean is 0,000 meters, 0 hundreds, 0 tens, and so on and so on. That would be insane. So this zero is not significant. It disappears when the number is stated in scientific notation. This measurement has 4 significant digits. Next, look at 0.000015 seconds. Are the zeros placeholders? You bet they are, so they are not significant. Let's put the number in scientific notation and watch the zeros disappear. In the number 56.08, the zero is significant because it's between two significant digits. For the 8 to be estimated, the zero had to be measured. Again, let's put the number into scientific notation. The zero remains, so it must be significant. This number has 4 significant digits. The next one is easy. When the number is in scientific notation, just count the digits. They will be significant. That makes 2 significant digits. If the number had been 8.30 times 10 to the 3rd power, there would be 3 significant digits. Remember, if a zero remains when a number is placed into scientific notation, the zero is significant. The last one is a little tricky. Ask yourself, what's the purpose of the zeros? Are they holding the decimal place? Let's cover them up and see if the magnitude of the number changes. No, it's still 132. So the zeros must be serving a different purpose. They must be significant. This number has 5 significant digits. Watch what happens when we put the number into scientific notation. the zeros are not replaced by the power of 10.
So what do you do when a zero is two things at once, a decimal holder and a measured or estimated digit? Suppose in this measurement, the 8 and 6 are measured, and the first zero is estimated. There are two ways to show that this zero is significant. First, you could put the number into scientific notation and keep the first zero. Or you could use another physics trick. Put a bar over the last significant zero. This tells us that there are 3 significant digits in our measurement. If the bar were over the second zero, there would be 4 significant digits. The only time you'll see the bar is in a number with no written decimal. They are not necessary after a decimal because it will be obvious whether the zero is significant or not. Now it's time for some practice. Your teacher will show you some numbers. Decide how many significant digits each number has. Try these by yourself. Sometimes the best way to learn is to make mistakes and then correct them.
Local teachers, please turn off the tape and give students this problem set number 1 from the Facilitator's Guide.